Hello, I'm Todd Gamblin from the Advanced Technology Office in Livermore Computing, and I lead the Spack project. I'm going to talk about Spack on ARM. If you're not familiar with Spack, it's a flexible package manager for HPC. It's very easy to clone and just get started running. You can clone it from the URL here. And to install a package, all you do is you just say Spack install HDF5. And what it does is it simplifies installation for HPC. It pulls down HDF5 and all of its dependencies, it builds the dependencies, it builds HDF5, and you can use the library. Spack's gotten to be very popular. It's used in labs, academia, and industry. And we have thousands of users now. When we started the project in 2013, it didn't really start getting going until later in 2015. And we started getting contributors from across the community. And so you can see here in this graph that lots of different organizations contribute to Spack now, and it continues to grow. We've just surpassed 5,000 software packages in Spack. We have over 680 contributors, and at least according to our documentation site, we have over 3,200 users now, and they're all over the world. These are hits on our documentation site from lots of different places. Spack packages are very easy to build on different systems, so they are parameterized with a simple Python DSL. This is showing the KRIPKey package, and KRIPKey is it's a deterministic SN transport mini app. It tells you where to download KRIPKey, where to find more information about it, and then these here are versions that you could download of the package. These are variants, so these are different build options. This tells you the space of things that you could build, so you could build any of these versions combined with MPI on or off and OpenMP on or off. And then there are dependencies, and some of these depend on what variants you've selected. So if you turned MPI on, then the package depends on MPI. It says when plus MPI. If you turn MPI off, it doesn't use MPI, and it just builds a plain version. So you can see there are lots of different ways you can build this, and it's just one simple recipe. The build instructions are similarly generic. Down here, this says what CMake arguments to use for the particular configuration. So self.spec here is the configuration of the package. If OpenMP is on, then we enable it. If MPI is on, then we enable it. If not, then we disable them. And then the install method, this just makes up for the fact that KRIPKey, which is a CMake package, doesn't actually have an install target. So we just copy the executable into the bin directory. This is a fairly simple package. They can be much more complicated, but you can see, there's this division between what's possible and how to build it, and they're written generically. They're not tied to a particular tool chain, and they don't make a lot of assumptions about the platform. And so that enables us to compile Spack packages on a wide variety of architectures, including ARM. Finally, Spack's syntax lets users leverage all of that parameterized goodness in the packages. If they just want to get a package installed like HDF5, they can say install HDF5. That's unconstrained. They can install particular versions. They can install a package built with a particular compiler. So you could pick ARM's compiler, or you could pick GCC, or you could pick Clang. You can provide these options. So this is like the MPI option that we saw in the package. C++ support for HDF5. You can inject flags into builds, which is handy for HPC if you want to test different optimization settings. You can target specific microarchitectures, so we have support for that. And you can specify any of this stuff for dependencies. The syntax is recursive. And so that lets you very easily play around with packages, get them working on new platforms. And so it puts Spack in a nice position to support ARM, because there's really not all that much that we have to do with the packages to make it work. So we aim to support ARM for HPC because we've seen what everyone else has been seeing. There are lots of performant ARM chips starting to come out. So ThunderX2 has been in Isambard and Astra for a while. Graviton 2 is in AWS now and has really good price performance compared to some of the x86, 64 options. And then obviously the Fugaku machine is now #1 in the world. The software stack for ARM has grown in leaps and bounds, and so Linux on ARM doesn't look that different from x86, 64, and it's increasingly easy to build on ARM systems. And we think Spack's in a good place to support ARM. The recipes don't require a lot of rewriting. Most of them have only required some patches to get working for ARM, and they're parameterized. They're not tied to a particular toolchain, like I said before. So a lot of users have just grabbed Spack and gone on ARM systems. And what we've seen, and I'll talk about later in this presentation, is that a lot of those contributions have just started flowing back into the Spack repository. And that's appealing because you can use the same tooling without different files or different configurations or anything like that across x86, 64, ARM, Power, all the different platforms that you want to try out. So we hope that Spack serves as kind of a common tooling to enable you to try out new platforms, so that you can pick the architecture that gives you the best cost performance without worrying too much about resurrecting the whole software stack on a new system. Spack is in fact used on Fugaku. It's used on the top 3 systems in the world right now. So that's Fugaku at RIKEN, and then the Power 9 Volta systems at Oak Ridge and Livermore. We've been working with the team at RIKEN and Fujitsu for over a year now, maybe a year and a half, 2, as they have tried to build all Spack packages on Fugaku. They're using Spack to provide open source software for users on the machine. And their first step to doing this was they basically just took Spack and they tried to build all the packages with all the different compilers they cared about. And so they have this website that you can go to here, postkWeb rccs.riken.jp/open source software/public. And you can see the result of every one of their builds. And I think the cool thing here is that when compared to their success rate with the with builds on x86, 64 with GCC, with GCC on ARM, they're almost as good. So I mean, they're getting 78% of the packages building on ARM with GCC, and they get 81% on x86, 64. So it's not that different. The ecosystem is about the same on ARM as it is on x86, 64. And Spack made it very easy for them to do this compiler testing campaign because, like I said, they just plug in different compilers. They build it with %Clang on ARM, they build it with %Clang on x86, 64, and so on. All right. RIKEN is providing open source software to users with essentially 2 Spack instances. They have a set of core system packages in their system Spack instance, and this is the stuff that most everyone needs. They have a user Spack instance with a lot of more HPC focused packages, and they use chaining to hook these 2 things up. So essentially what that means is that this Spack instance is using the packages over here in the initial system packages, so the core compilers, Java installations, and so on, as dependencies. And that's something that you can configure with Spack with our chaining feature. Users can also install their own instances of Spack and chain against both of these system instances. So we hope that this helps people on Fugaku really take advantage of the system. It's a relatively small number of packages, especially compared to the thousands that the RIKEN folks built that are available right now. But they're planning to expand this as the system is open to more users. There's been a lot of work on Spack at Sandia as well. On the Astra system, the folks at Sandia developed what they call ATSI, the Advanced Technology Software Environment. And that essentially is the user environment on Astra. It's all the HPC software, the MPIs, the compilers, the math libraries, and so on. And while the first version of that was done with RPMs, they have prototyped a Spack version that adds actually some multi-user features to Spack. And so this was actually presented at HPC SysPros last year, and we're working on integrating these features into mainline Spack. So you can expect to see this sort of system user distinction that's on Astra and on Fugaku come into mainline Spack soon. It may not be in the 0.16 release that's coming up right now, but we expect it'll be in 0.17 right after that. TriLab users, so the code teams at Livermore, Los Alamos, and Sandia are building their applications on Astra with Spack. It's used pretty heavily on that machine. And so I think it's helped users out. It's allowed them to bring their software stack with them and build it on the machine for ARM. Community contributions have been key to ensuring that Spack packages work on ARM systems. If I count, if I just search for ARM in the Spack repository, I find about over 100 PRs that have to do with ARM. But if I look at the users who are contributing packages for ARM, I counted over 400 different pull requests that had something or other to do with ARM. So it's really a lot of contributions that are coming back into Spack from these systems. So obviously from RIKEN and Fujitsu, the teams there have done lots of patching of packages to make sure that they build. That's how they got their success rate with the compilers up so high. It wasn't initially. There have been contributions from ARM itself, so compiler support. We had over 400 commits from one user who's contributed a bunch of packages, but also a number of patches specifically for ARM. And that's this Darmac user from High Silicon, which I believe is a Linaro member. And so they've contributed an awful lot to the ARM ecosystem. And then finally, NVIDIA has actually contributed their compiler support for their HPC SDK to Spack. We're working on integrating these. These were formerly the PGI compilers, but now that NVIDIA owns ARM and the HPC SDK works on ARM, I think this will be interesting to folks. The main thing that we will be doing to support ARM better over the next year is we're expanding continuous integration in Spack in general. So this isn't just for ARM, it's for lots of different platforms. But we have started testing pull requests, and we tested on the E4S distribution, so you can go to e4s.io here. That is the Extreme Scale Scientific Software Stack. It is the US Exascale Project's essentially distribution that's built on top of Spack, and it's about 60 core packages and 250 packages with dependencies that you can build. And what we've started doing is for every Spack PR, we are testing all of these E4S builds on that PR. So if anything changed about a package that's in E4S, we'll rebuild it and its dependence in a GitLab pipeline. And we have support in Spack for essentially generating these things out of an environment. And so that whole E4S package is defined in an environment that looks like this. We send it to GitLab, it generates a pipeline, and we run that on PRs. Right now, we are only able to do that for PRs that originate from the Spack repository for security reasons. That's because PR code is potentially untrusted. And what we have been working on over the past year is expanding this. And so we are adding security features to our Spack CI that will enable us to build code from forks in essentially a sandboxed environment. And we'll build the package in a separate build with its own binary mirror. And then once that is used to verify that the package works, once a human has approved it, we will build a binary package for that thing again on develop in a more secure environment. And so what this is going to enable us to do is not just test E4S on things that make it into develop or things that come from the core Spack repo, but we'll be able to test on every PR and really keep this stack robust. So we are expanding the pipeline to include more PRs, and once that is done, we're going to start expanding the number of architectures that we support. So right now we have builders running for x86, 64, and Skylake, but we're running in AWS for many of these builds, and so we will likely have Graviton 2 builds done for many common OS images in containers. And then at Livermore, we are starting what we're calling our green test cluster, where we would build every PR on a set of nodes that are sort of outside our core network so that we can build untrusted stuff there. And that will enable us to include many more architectures. So we anticipate having AMD, Intel, Power, and ARM nodes. And the ARM nodes may include things like ThunderX2, and I believe we're going to have an A64FX node. We'll see. And like I said, the AWS builders will eventually include Graviton. So hopefully with this, you'll be able to build, to not build Spack packages and to install things straight from binaries. So for more on this and for more on the latest Spack release, come to our BOF. Our BOF is on Wednesday, November 18th, so that's next week, from 11:30 a.m. to 12:45 p.m. Eastern. And we will be announcing Spack v016, and we'll have a lot more news for you there. Thanks.